So good morning, everyone. My name is Mostafa. This is John, and we're representing Group 14, and we'll be presenting on our project for developing a lightweight and high-performance alternative for long-term oxygen therapy. So first, some background to understand the problem we're targeting. This graph here on the screen shows the top 10 leading causes of death around the world today. 3 of these top 10 causes are lung diseases, which account for 8 million deaths in 2015. That's 14%. So this is a very large number, and these diseases are very prevalent. So one problem that is common amongst all of these diseases is a condition called hypoxia. So once a patient's lung function deteriorates, eventually it gets to a point where they're not able to get enough oxygen into their blood. And the reduced amount of oxygen in their blood has a variety of consequences. It results in very rapid fatigue onset. So these patients get tired very easily. So even for a patient to walk from one part of their house to another across the hallway can be extremely tiring. And even carrying conversation for a lot of people is not possible. Stay there. So it also results in poor memory, loss of concentration, and the loss of sleep, and it increases the risk of heart disease. So the solution to this hypoxia problem is the focus of our design project, and that's oxygen therapy. So oxygen therapy is a technique in which pure oxygen is provided to the lungs of a user through a nasal cannula. So that's the tube hooked up to the machine leading to the lady's nose in the picture. So this pure oxygen increases the amount of oxygen in the patient's lungs and allows them to get enough oxygen into their blood. This solves the problems of hypoxia, improves the amount of exercise they can do before they get out of breath, improves memory, concentration, sleep, and reduces the risk of heart failure. So oxygen therapy is a good thing, but there are some very significant problems. Oxygen therapy really limits the mobility of patients. So as you can see in the picture here, a patient must have a source of oxygen with them wherever they go. And so even if they're going outside for a walk, they need to carry some sort of oxygen source with them. For a lot of people, it's a heavy oxygen tank like you see here in the picture, or for others, it's a portable device that produces oxygen from the surrounding air. In either case, they're very heavy and bulky, and there's only a limited amount of time that they can actually stay outside for. So either the battery runs out or the oxygen inside runs out within 2 to 4 hours on average. And this really limits the freedom of these patients. It confines them to their home, because for a lot of these patients, even going outside for lunch, going outside to go to the doctor, to visit family is not possible anymore because they're going to run out of oxygen. And so this is really the problem that we wanted to address in our 4th-year design project. And this is also the problem that we're addressing through our startup company, VivaSpire.
Okay, so the customer requirements that we've identified, the primary and most important ones are that we maintain the utmost important oxygen supply rate. So the people who use these devices need a certain oxygen flow rate and percentage in what they're getting through the nasal cannula. The weight needs to be reduced because, obviously, what Mostafa mentioned, battery life is also a restrictive factor in these devices. You need to constantly make sure you're getting enough oxygen and you have time to get home to get the oxygen you need. The purity of oxygen goes with the oxygen flow rate. You need oxygen to be at least 87%. The secondarily most important aspects, we need to be able to select which oxygen flow rate, so 1, 2, 3 liters per minute. Whether it's pulsed, so pulse means if you're breathing in, you get oxygen only when you're breathing in, as opposed to continuous flow, which is just a constant supply of oxygen. The dimensions need to be reduced because it's difficult carrying around a large, bulky device. It needs to be easy to use. So right now, the devices that we're going to replace weigh about 10 pounds. They last 1 hour. They do give you 87% oxygen, and the 2 liters per minute is what most people require. So our device is going to be a fraction of the weight, almost half. It should last 4 times as long and still maintain that oxygen percent and flow rate. The way that these work, the ones that we're replacing, they take in air, and then you can see in the diagram there's a compressor, so they work by a change in pressure. Once the air is pressurized, there's two columns where there's zeolite material, which absorbs nitrogen. So the nitrogen is removed, and the oxygen is what's left over and gets supplied to the user. However, there's a trade-off in these devices. Obviously, the higher your flow rate, the larger compression you need, larger compressor, heat exchanger, whatnot, your device is heavier. So we need to build a lighter and more efficient device. In order to do that, we need a material that concentrates oxygen, not by a change in pressure, but by a change in temperature. So as you can imagine, our device is going to still intake air and spit out oxygen. But in order to do that, we need this material inside it that at room temperature absorbs oxygen. And then what we do is we heat it, and then the oxygen is released and can be supplied to the user.
So this oxygen-absorbing material that John mentioned forms the core of our technology. And so we investigated several different candidates to use as this oxygen production mechanism. And we've labeled them A, B, C, and D here, just not to disclose for company protection. Each of these materials were also modified in order to optimize their properties, oxygen production properties, using two solvents, number 1 and number 2. So I'm going to go through here like a rundown of all the results that we have and how we came up with the final material to use for our prototype. So compound A is shown here. The graphs here are from TGA, thermogravimetric analysis. Basically, it's a characterization method where you take a material, you heat it through a range of temperatures. So for us, it's the operating range of a device, how far we'd heat it for, and you measure changes in its weight. So when the material decreases in weight, you know that it's released oxygen and it's producing oxygen for the user. In this graph, for compound A unmodified, the graph on the left shows that within the regular operating range of a device, there was no oxygen released. The only decrease in mass that was observed was due to material decomposition at very high temperature. So unmodified compound A did not work. Then we chose to modify the compound A using a solvent, recrystallization in solvent 1. What this graph again shows though is no decrease in weight, so there is no oxygen production. However, when we recrystallized in solvent 2, we were able to achieve oxygen release. We got a release of 3.5 weight%. So this basically means if you have 10 grams of your oxygen absorbing material, it will produce 3.5 grams of oxygen for you, and that works out to about 2 liters of oxygen. One key thing to note here, though, is that in addition to releasing oxygen, the material is required to reabsorb the oxygen in order to be ready to supply the oxygen again to the user. So basically, it's a repetitive process. You need to release the oxygen, reabsorb it, and then release it again so that the user gets a continuous supply. It's not just little bursts. So for that specific material, we saw that it took 2 hours, which was too long, and we need a 10-minute reabsorption time. The next thing we did was analyze the oxygen purity coming off of the material. And we found that this was 64%, greater than 64%. However, current devices require at least 87% oxygen. So next we moved on to the next material and analyzed its properties. Compound B, unmodified, again, did not show any release of oxygen within the operating range temperatures. However, when crystallized in solvent 2, we did see an oxygen release of 2.85%. However, once again, there is no reabsorption of the oxygen, which is required for the device to work. Next, we looked at compound C. So it's another material, and we did see some very unique properties. So this is unmodified material, not recrystallized in any way, and we saw an oxygen release of 3.4%. Over the operating range of a regular device. And the release profile was also very different, so it's a more gradual linear release as opposed to a very steep one. Okay. The next thing we did was modify this material, but in a different way. So what we did was reduce particle size by crushing. And we found that the oxygen capacity increased to 5.25%. So there was a material benefit that we saw just by crushing the material in our lab. And the the hypothesis that we're going forward with is that with making it into a nanomaterial would improve the properties even further. Next, we looked at oxygen reabsorption properties for type C material. So like I mentioned, in order for the device to be able to work, you have to reabsorb the oxygen after you've released it within about 10 minutes. And we saw in this graph that that was possible within about 10 minutes, from about 37 minutes to about 47-ish. There we got about we got the reabsorption we're looking for. However, the capacity of the material did decrease. So whereas in the first heating it released 5.25% oxygen, the second time we did it, it only released just under 3%, and then the third time there was a little less than that. So there is a slight decrease in the oxygen capacity between cycle 1 and cycle 2, and a large decrease after the initial cycle. And this is something that for similar materials has been shown. There's like a break-in process. This is a summary of the different data we collected for the different materials. And basically, it shows the oxygen capacity of each material. We ended up choosing type C material that was crushed because it provided the largest oxygen capacity, which would allow us to make the lightest and most efficient device. In addition, it reabsorbed the oxygen within 10 minutes, which was a critical requirement. So this is the material we went forward with for our prototype.
So a little bit about the prototype, just an overview. It's very simple. We have two valves. So you can imagine over here there's air, ambient air, coming in. So flows through our nanomaterial. The oxygen is then removed from the air, and then the air flows out. So we have a three-way valve up here that the air is purged out of. And we continue that until the material is saturated with oxygen, at which time we press a button. The two-way valve closes, so we don't take in air anymore. Then whatever oxygen is stored inside of our material is released because we have heating coils inside of the tube. The three-way valve then switches, and we can fill up an inflatable chamber. And then so we've tested it, and this you can imagine would be a patient someday, inflating. It's fairly slow, but yeah, you get the idea that it worked. So we were able to fill up a balloon with about 1 liter of oxygen. You can see here, this is our tube filled with our compound C. And then just checking the oxygen percentage. The percentage is on the screen there. It's only 32%, which is attributed to leaks within our system. We had very poor joints on our tube connects. And then over time, the oxygen percent slowly goes down because the oxygen is desorbing from the material as we run it. And I've already, yeah, so the leaks we saw. Now the weight, okay, so this is the key. We're only 600, just over 600 grams. Now this is something that would feel like clothing if you have to carry it with you, as opposed to something that's 10 pounds, or maybe that would be about 4,500 grams.
So now I'll go through a little bit of the commercialization we're looking to do with our company. So one of the first things that we did for this project was to talk to, they're called vendors of record here in Canada. So for oxygen therapy, a doctor will write a patient a prescription, and they'll go to a vendor of record and speak with them in order to get fitted with the right oxygen therapy equipment. So these two vendors were ProResp and Respiratory Home Care Solutions, and they really guided us in terms of focusing on what key problems to solve in the industry. And this is what gives us confidence that the problems we've chosen in this industry are the right ones to solve at this time. Another reason why this solution is really required right now is because the use of oxygen therapy is expected to increase rapidly over the next few years. So it's an 8.5% growth rate. The current market value is about just under $3 billion, and it's going to increase to more than double that, to more than $7 billion by 2024. So going into this market, we're going to be targeting portable oxygen concentrators within the oxygen therapy market, and then we'll be expanding into other markets as well, such as recreational activities, things like mountaineering, oxygen bars, even underwater, or even for space travel one day. And helping us along the way have been a key group of advisors. Dr. Chung and Dr. Lee from chemistry have advised us on the chemistry, getting the material to work, and also several other people like Jen Coggin from the nanotechnology engineering department. We'd like to thank them, as well as the entire nano engineering program and Velocity Science as well for the support along the way. So our startup company name is Vivaspire, and we want everyone to reach further. Thank you.
So connect this.
Time for a quick question.
Yes.
So the oxygens that we produce,
Yes.
will it also be at 60 degrees? Because you have to use
So-
the oxygen.
So on board
Right.
it's 60 degrees, and then as it's released, it'll flow through a narrow tube where the heat will dissipate
Yeah.
before it gets to the user. It should be about room temperature. Once you
And,
bring it in.
and oftentimes there's a storage compartment as well for the oxygen, and that cools it as well.
What's the reason there's less oxygen produced each cycle?
So the material we're using oxidizes, and that changes the structure of the chemistry changes, and then it doesn't absorb oxygen.
And so you have to refill the cylinder, like with the material has to be replaced, or it can be, deoxidized?
Yeah. So the way we're going forward, our business model is so that you have clip-on cartridges that are full of our material. They will last about 2 months. Then at which time you clip it off, send it back to us. We will recycle the cartridge, and you get a new one. So it does degrade over time. Initially, it's very quick, and then it's a very gradual decrease for about 2 months.
Okay.
Yeah.
How does the cost of your solution, your product, compare with the current one?
Current solutions are about $2,000 to $3,000 for a portable oxygen concentrator that you can carry around with you. Ours, we've priced it out to be initially about $400. That way we can expand, our main revenue will come from the sale of cartridges. Yeah, and which will still be cheaper. In the long run, it may even out, but in the short run, it's much cheaper. Yeah.
Okay.
Thank you.